Hello, I'm going to be telling you how to compute half-integral duals for the uncrossable cut cover problem and to show you how this could be used to compute half-integral flows in what are called Seymour instances. This is joint work with Nikhil, who is also at IIT Delhi. So let me first tell you what the 2H connectivity augmentation problem is. So I'll give you a graph undirected. The edges are blue and red. The blue edges are the set E. The red edges are F. We later call the blue edges the demand edges, the supply edges, and the red edges the demand edges. Now what we want is we want to find a subset of the blue edges, the subset of E, of minimum cost such that every red edge is in a cycle in E prime union F. So in this so in this example, if you look at the dark blue edges, then they form a subset E prime such that every red edge is in a cycle. If I look at the red and the blue, the dark blue edges together. Yeah, so this red edge is in this cycle, and this red edge is in, and so on and on, right? So this red edge is part of this cycle. So, okay. Now, there's another way of formulating this, and that is using requirement functions on sets. So let f be a requirement function on subsets of vertices, which is a 0, 1 function, and it's getting defined as that a set of vertices has a requirement of 1 if there is exactly one red edge across the set of vertices. So, so for instance, these dotted sets here are actually the sets which have requirement 1. So this has a requirement of 1 because there's one red edge across it, and this has a requirement of a 1, this singleton set, because there is exactly one red edge across it, this red edge. And similarly, this set with 2 elements has a required 1 because there is exactly one red edge across it. And so with this formulation, the problem can be thought of as finding a minimum cost subset of edges E prime, which is a subset of E, such that the number of edges for any set S, the number of edges in delta S intersection E prime, which means number of edges that we have picked which cross that set S, is at least as large as the requirement of that set, which is 1 if there is exactly one red edge across the set and 0 otherwise. And we will refer to this problem as the 2H connectivity augmentation problem. And here, once we have this requirement function on the sets, then we can actually forget about the red edges, because the requirement function actually captures those sets which have exactly one red edge across them. So now we can just view the problem as saying, well, I have given you some sets of some sets with requirement 1, and pick a minimum weight collection of subsets E prime such that every set which has a requirement of 1 has at least one edge of E prime across it. And we'll call this the 2E cap problem. Let me now tell you what an uncrossable function is. A function f is called uncrossable if for every subset, again, this is a function on sets of vertices in a graph, and it's a 0, 1 function. So if I take any two sets of vertices, then if the value of the function is 1 on both of them, then either it means that the value of the function on A union B and on A intersection B is also 1, or it means that the value of the function on A minus B and B minus A is also 1. These functions have come up many times in network design in the past, and a lot of network design problems have requirement functions which are uncrossable. And it's no surprise that for this problem too that we are considering, it's the requirement function that we defined earlier on the previous slide, which was the requirement is 1 for a set if and only if there is one red edge across that set. That's also an uncrossable function. And now if f is an uncrossable function, then the 2H connectivity augmentation problem can be formulated as an integer program. And on the right is the dual of that integer program. So and this is a fairly standard program, so let me just quickly go over it. So what do we want? We want to pick, so xe is an indicator variable which is 1 if we are picking the edge in E prime and 0 otherwise. And so we want to minimize the total cost of the edges that we pick. And What do we want? If I take any set of vertices, then the sum xc e belonging to delta s will be the number of edges in delta s which go across the set that we have picked, and that is at least as large as the requirement of the set. Okay, and the dual here is that you want to associate a dual variable with every set S. So y sub S is that dual variable, and you want to maximize summation of Ys such that the assignment of values to the dual variables forms a packing. Right. So this is the packing condition here, that if I look at any edge in the graph, then the total the sum of the dual values of the sets which this edge goes across. So these are the sets which this edge goes across. The sum of their dual values is at most the capacity of the edge, and these values have to be non-negative. So this formulation was used by Williamson, Goemans, Mihail, and Vazirani to show a primal dual algorithm for this problem, and they showed that you can compute a set of edges E prime of total cost at most 2 times the value of the dual solution. So they actually also built a dual solution, Y, and the cost of the edges is less than 2 times the value of the dual solution. So this implies a 2 approximation for the 2-edge connectivity augmentation problem. We are interested in something slightly stronger, and that's what this talk is about. Here we want that the dual variables should have half-integral values, and that was of course something that was not considered by WGMV and was also not part of the paper. So let's quickly go to what the WGMV algorithm is. The algorithm is actually very simple. It says a set is called unsatisfied if it has a requirement of a 1, but there is no edge in E prime. Recall E prime is a set of edges we are picking, and so there's no edge in E prime that goes across the set S. And so the algorithm begins by identifying all the unsatisfied sets, in fact the minimal unsatisfied sets, and it raises the dual variables corresponding to these minimum unsatisfied sets. And when you raise these dual variables, remember we have these packing constraints associated with the dual variables, so you can't raise them arbitrarily. Some edge will go tight, or some constraint will go tight, and then when some edge goes tight, we take that edge and we include it into set F. The final set of edges F after some pruning will be the set E prime that we are interested in. So for now, I'm going to think of it as F. So the algorithm is just this. At any point, you find the minimal unsatisfied sets, and you raise the dual, and the moment an edge goes tight, you include it into F, and you recompute the set of minimal unsatisfied set. And you keep doing this until all sets become satisfied, and then there's the second phase. So this phase is called the growth phase of the algorithm because you're growing these dual variables, and then you have a reverse delete phase in which you consider edges in the reverse order in which they were picked, and then you drop an edge if it's not needed to ensure feasibility. So that's the WGMV algorithm in a nutshell, and let's quickly run it for a small example to understand what the issues are. So this is the example. So recall the red edges are the edges. We want to pick blue edges such that every red edge is in a cycle, and so these are those red edges. And so recall that we defined sets which have requirement 1 as those which have exactly one red edge going across it. So this singleton set which is C, the singleton set which is D, and singleton set which is E all have requirement 1. And they are initially the minimal unsatisfied sets. A would not have a requirement 1, and B would not have a requirement 1 either. So initially we will be raising the dual variables in the very first step, raising the dual variables for set C, D, and E. And then we're going to view it as a process in time, or WGMV view it as a process in time. And then when these dual variables have increased to a half, then the edge CD goes tight. And when the edge CD goes tight, then C and D, these two sets become satisfied. And now the minimal unsatisfied set is BCD. That's this bigger oval here. That's an unsatisfied set, and it's minimal unsatisfied. And of course, E is still an unsatisfied set. So we continue increasing the dual variables. And note at this point, right, so at time half, this edge BE is already feeling a dual variable of half from this end. So it has a residual length of only half. Okay, by the way, I didn't mention, but all of these edges, the blue edges, have length 1 here in this example. So this has a residual length of half, and so these two duals, the dual BCD and the dual E, can increase only to an extent of 1/4 now. And so at time half plus a quarter, which is 3/4, this edge will go tight and the algorithm would stop. So our algorithm would actually pick up both these edges, which is the right thing to do. But now I want you to think about what the dual variables are. So C had a value of half, D had a value of half. The dual variable corresponding to the set BCD had a value of a quarter, and the dual variable corresponding to the set E had a value of 3/4. So clearly this is not a half-integral solution. Now, there is a subclass of uncrossable functions which we call proper functions, and this was considered by Goemans, Williamson in their paper from the early 90s. And the requirement function f is called proper if I take a set which has requirement 1 and I break it up in whichever way I like, then one of those pieces needs to have a requirement 4. Then we would say that the function is proper. And proper functions are a special case of uncrossable functions. And the Goemans-Williamson algorithm for proper functions yields half-integral duals. And why am I telling you this? Because this was sort of our starting point. This was our motivation to try and see whether we could extend this this property of the Goemans-Williamson algorithm also to WGMV. And just 2 lines about what the GW algorithm is. It's very similar to the WGMV algorithm, and at any point, the set of tight edges that we have, they form a forest, and the components of these forests which are unsatisfied are called active sets, and the other sets are called inactive. And we'll use that in the next slide. So let's quickly say why in one slide the Goemans-Williamson algorithm for proper functions gives a half-integral dual solution. And there are many ways of proving this, and here is a way of doing it, which we will then be extending later. So let's define the parity of a vertex V inside a set A as the parity of a vertex V in a set A. Let's define it as the total dual that this vertex V feels from subsets of A. So ys V belonging to S. So V is in the set S and S is a subset of A. So there's a total dual that this vertex feels from subsets within A. And we are looking at the fractional part of this. You know, this total dual might have a value 3.5. So we are interested. So the parity then of this vertex is half. And if this total dual is value 4, then this parity is 0. And I'm using these numbers because we will always have vertices with parities only 0 and half. And that's what we want to prove. So now if I take any active set, so an active set always contains a vertex which was always part of active sets. And if it was always part of active sets, then that means that the parity of this vertex is the same as the parity of the value of time, right? If t is the current time, then whatever is the current time, look at its fractional part, and the parity of that vertex is the same, because this vertex was, always inside some set whose dual was increasing with time. And so now, so I'm going to do this proof by induction, or I'll sketch the proof by induction. So we are arguing that all vertices have the same parity, and this parity inside a set have the same parity, and this parity is either 0 or half. So now consider, let's say you have 2 sets, and these are both active sets, and they have. So our induction hypothesis is that both of these have, all the vertices in these 2 sets have the same parity. And what will that parity be? That parity will be the parity. Remember, there is a vertex in each of these sets whose parity is the current time, whose parity is the same as the parity of the current time. And so So that's what we said. Now these two sets combine along a tight edge E. Let's E equals UV, and the parity of U and the parity of V is the parity of the current time. And since the length of this edge is integral, it would mean that the time at which they combine would be either would have parity either 0 or half. Okay, and then at that time all the vertices in these two sets would also have parity, which is the time, and so the resulting set that is formed will have all vertices having the same parity, which is the same as the current time. So this was the easier case when two active sets combine, but one can similarly argue that if you have an active set and an inactive set combining, then the property is true that the resulting set all vertices have the same parity, which is the same as the parity of the current time. Okay, so now let's okay, so why is that parity thing important? So if the parity always remains the same for every set, then you can see that the extent to which the dual variable would increase would also be half integral, right? Because it says that all our events that are happening at half integral. By events I mean the times at which two sets combine. They are all happening at half integral multiples, and so the duals that we would have increased would also be half integral. Let me now get to the WGMV algorithm and say say a few words on what we did there. So we had to strengthen the analysis of the WGMV algorithm and then also modify it to take care of these kind of parity considerations to eventually be able to get the half integral solution that we need. And so here in this I'm showing you so these circles and ovals that you see are unsatisfied sets in various iterations. And if I look at any particular iteration, so let's say these are the minimal and unsatisfied sets at a particular iteration, and they are shown in gray. So these are the active sets, and we would be increasing the dual variables corresponding to these sets. And once an edge goes tight, I will show that edge. So the label on the edge is the step. So let's say at the end of the first iteration, this edge here went tight. And these are the two sets that this edge was running between, and I'm going to give a label which is equal to the iteration at which the iteration at which the edge the set became satisfied. So this set becomes satisfied at the end of iteration 1, and so it gets a label of 1, and this edge also got tight in iteration 1, so it gets a label of 1. And so we are going to continue this. And once a set becomes satisfied, we are going to change the color to something darker, and so it becomes a darker shade of gray. And so at the next step, let's say this edge goes tight, and so that gets labeled 2, and this set got satisfied at step 2, at iteration 2, and so that's labeled. And so we go on. Maybe at the next step, this edge went tight, and this set became satisfied. And at the next step, this edge went tight, and this edge became satisfied. This set became satisfied. And now, okay, note something that happens if all of these sets are satisfied, then the minimal unsatisfied set becomes this larger oval, and so that gets a color of gray. Okay, and then at the next step, let's say this edge went tight, both of these sets got satisfied, and once again you see that all of the sets within here are satisfied, and so this becomes the new minimal unsatisfied set. So in this iteration, which means that after the end of the 5th iteration, the minimal unsatisfied set are these 3 sets. And now maybe in the next step, this edge goes tight, and when this edge goes tight, this set as well as this set becomes satisfied, and so that's why the color changes to a dark. At this point, note that this is the only minimal unsatisfied set here. And then at the next step, let's say this edge went tight, so this also became satisfied, and now this is satisfied, this is satisfied, this is satisfied. So the minimal unsatisfied set is the big oval now. And let's say this was not the entire graph, there were other things happening, so this now becomes a new minimal unsatisfied set, and we'll continue the procedure. Okay, so now I want to say a little bit about what is our alternate GMV, alternate analysis for WGMV. So what we do is we'll be constructing a tree, and what is that tree going to be? It's basically laminar, the unsatisfied set, the minimal unsatisfied sets that we encountered during the WGMV algorithm, and that's a laminar family. So there's a tree corresponding to it, and we look at the tree corresponding to those sets which have labels greater than or equal to I. So let's say S sub I is that collection of sets which have labels at least I, and Ti is the tree corresponding to them. So here in the right, you can see a picture. I'm drawing the tree T3. So this node of the root of the tree here, it corresponds to the big set here, which is going to have a label which is only larger than actually 7, because it would have gotten satisfied in some later iteration. I have not put down what that iteration number is. And then it has as children these 3 sets which have labels 7, 6, and 6. So those are those 3 sets there. And then this will have, in this particular tree that I'm drawing, remember I'm only including the sets which have labels 3 or more. So this is T sub 3. So I'm not going to be including these 2 sets with labels 1. I'm only going to include a set with label 4. So that's there. And similarly, this on this node here, I'm only going to show the 3 sets which have label 3 or more. So this is 5, 5, and 3, and I'm going to ignore the 2. And so finally, this 6 does not have any child, so it remains as is. Let me also show you the edges that are of interest to us. So F is the set of edges that were picked by the algorithm. I think earlier on one of the slides I said E prime, but now let's just call it F. So F is the set of edges which are picked finally by the algorithm, and let's say F sub I is that subset of F which have labels at least I. So once again, we are talking of 3, I is 3. So in T3, I'm showing here those edges which have labeled at least 3. So there is this edge which is going from this set labeled 4 to the set labeled this set labeled 1, but now this set labeled 1 is not there, so it's going to the set labeled 7. So that's why this edge is drawn like that. So this is that edge with label 4. Similarly, this edge with label 7 is going from the set labeled 7 to this outer thing, which is this root here. So that's the edge labeled 7. And similarly, we have drawn the edges corresponding to this edge labeled 5, this edge labeled 3, and this edge labeled 6. And so they're all here. Great. So now what we are going to, okay, so now let me focus on one particular set, and this had a label of 6, this set S, and it had these 3 children in T3 which had labels of 5, 5, and 3. Recall it had one more child, but that had a label less than 2, and so we are not interested in that for now. We are going to be doing this with every iteration, and so depending upon which iteration we are talking of, some sets are not of interest to us. So we are talking of iteration 3 here, and which is why the sets with label 2 and the edges with labeled 2 or less and the edges with label 2 or less are not of interest. Okay, now let's define alpha is, in this case alpha is 3, as those edges which have one endpoint in S, and that endpoint is not in any of these subsets. So that endpoint, so we're defining x3s as or xis as that subset of vertices which are not in any child of S in the tree Ti. So this is sort of the zone, the set of vertices outside, and alpha is are those edges which have exactly one endpoint in here. And note that if this were an active set in the third iteration, then in the third iteration, since remember we are only looking at sets with labels 3 or more, it would not have any subset in the tree. Because it would actually be a leaf of the tree T3, in which case alpha is all the edges which are incident to this set. And now I can recast what WGMV proved. They proved that the average degree of active sets in any iteration is at most 2. So this is of course their statement. By degree I mean the degree in the final set of edges F that we pick. In our words, we could say it as that if I look at the active sets, which is A sub I, then and I look at the degree of those active sets, which we just argued is alpha I, then the total degree of the active sets is at most 2 times the number of the active sets in iteration I. Why am I saying it in this manner? Because now in my next slide I'm going to show how we are going to strengthen it. And the way we are going to strengthen it is that this is the WGMV statement, and we are making a stronger analysis. We are saying that I can do the sum on the left not just for the leaves of the tree, the active sets in iteration I, but for all sets in this site, for all sets in SI. Remember, SI is the set, all those sets which have label I or more. And so this is this whole tree up there, not just the leaves. So we are looking at that. So we are, our left hand side is much larger, and to offset that we have to include something on the right hand side, and this is slightly technical and I'll not be able to go into more detail here, but what this is saying is so this is R sub I is the number of critical sets, and we call a set critical if the edges of F sub I induce a tree over. So let's take this example of a set S, and these are its children in the tree, and these are the edges of F sub I. So remember, we are still talking of iteration 3, so these are the edges label 3 or more. And now if I were to think of this as 4 sets of vertices, this set as 1, this as another, this as a third, and the remaining as a fourth, then these edges form a tree on this 4 set of vertices, of which x3s is a leaf. And when such is the case, then we call this critical. And those are sort of things that we need to handle specially and take care of them specially, which is why they show up on the right. And how do we modify the algorithm now? Let me quickly go over it. So what are we going to do is that every time a set becomes minimally unsatisfied, we will ensure that all edges incident to that set have the same parity. And what is that parity? That parity is the current time, the parity of the current time. And what does it mean for an edge to have a certain parity? The parity of an edge equals x, where x is the fractional part of x, where x is the sum of duals of subsets of S that E crosses. So, if I look at a set S and I look at an edge E that crosses that set, so let me look at all sets inside S, and let me look at the sets that E crosses there, and let's sum up all of those duals and any other reductions of length E that I might have done. Let me sum up all of those things and take the parity. That's the parity of the edge. And when a set becomes minimally unsatisfied, I'm going to look at all the edges that are going out of the set, and I'm going to ensure that all of those edges have the same parity with respect to the set S. And if some edge has a different parity, I'm going to reduce the length of the edge by half. Okay, so just to keep a picture right, every edge will have a parity of 0 or a half, and so if something has a parity which is 0, then I'm going to reduce its length by half. And so if I look at that example that I showed you earlier, then where things are going wrong, so here at time t equals half, this set and this set, so this became a minimal unsatisfied set. BCD became minimal unsatisfied at t equals half. Now at this edge with respect to this set has parity 0 at time t equals half. Why? Because it's not seeing any dual that I have raised. These are the only duals that I've raised inside the set. And so I need to correct this, and so I reduce the length of this edge by half. But when I reduce the length of this edge by a half at time half, then it already is feeling a dual of half on this edge. So this edge has become tight. So at time half, this edge also becomes tight, and so our process stops. And so the duals that we have raised is just this, which we raised to an extent of a half, this we raised to an extent of a half, and this we raised to an extent of a half. And so this is actually a half integral dual solution. So our stronger analysis will actually let us bound all this reduction in edge lengths that we are doing. And then we are able to prove this main theorem, which says that, if I give you a graph, an uncrossable set function, I can pick a set of edges such that those edges meet the requirements of all sets, and the total cost of those edges is at most the dual that I can build, where the dual is satisfies your packing constraint. Let me quickly, in the 1.5 minutes that I have left, tell you, why we actually came into this problem and what consequence does it have. So this is an interesting problem in multi-commodity flows on what are called Seymour instances. So for a multi-commodity flow, I'll call a supply graph as so I am given two graphs on the same vertex set. V is the vertex set. One is the supply graph, which is again the blue edges here, and the demand graph is the red edges here. And an instance is called a Seymour instance when G plus H is planar. And what is a multi-commodity flow? It's a flow between the endpoints of the demand edges, which respects the the capacities of the supply edges. So we assume that all edges, all supply edges have capacity, which in this example, in these examples, we are all going to be assuming is 1. And so this would be a valid multi-commodity flow. And it has to respect all capacities. We say that the flow is half integral if along any path the amount of flow that I'm sending is a multiple of a half. So we are interested always in finding the maximum flow. Here we actually have an integral flow, because I can send 1 unit of flow along this path, 1 along this, and 1 along this. And I have an integral flow of value 3, and I want to find the maximum integral flow. And if you look at this example carefully enough, you'll realize that this is also maximum integral flow. And if I want to look for the maximum half integral flow, then I could potentially route the flow like this. So on each of these green paths, I'm routing half a unit of flow. And this is so on, there are at most 2 paths which are using any edge, and this also has a value of 3. What's a multicut? A multicut is a set of edges whose removal disconnects every sourcing pair. So I'm thinking of the endpoints of an edge as a sourcing pair, and here if I remove these dashed edges, then every sourcing pair gets disconnected, and this multicut is of size 4 in this. And now interestingly, in the multicut, if I look at the multicut and I look at the multicut in the dual graph, then what I get, and I'm going to skip some slides, is that the multicut is a set of edges then, such that every red edge, which is the edge corresponding to the demand edge, every red edge is part of a cycle. And this is exactly our 2-edge connectivity augmentation problem. So the multicuts in the primal graph, their corresponding edges in the dual graph form a solution to the 2-edge connectivity augmentation problem in the dual graph. And similarly, there is a correspondence between the dual variables that we build in the 2-edge connectivity augmentation problem and the flows in the primal graph. So what is the correspondence? I can perhaps show you with an example. So if I raise this dual variable, and this is in the dual graph, in the planar dual that I'm raising this dual variable, then in the primal graph, one can think of it as routing a flow between the endpoints of this edge. And so the total value of the dual solution that we build is actually equal to the total the dual solution that we build for the 2-edge connectivity augmentation problem that we solve on the planar dual can be thought of as a flow in the original planar graph. And so there's nice correspondence, and this correspondence together with the main theorem that we prove helps us argue that the maximum half integer flow that we can send, remember this is so we have built a half integer flow, which is the half integer dual solution that we've built, and the primal solution that we built for the 2-edge connectivity augmentation problem is the minimum multicut, is a multicut. And so what we have shown is that we've built a multicut whose size is at most 2 times a half integral flow that we've built. And since any half integral flow is only going to be less than minimum multicut, so we have this side of the inequality and we get this approximate max flow min multicut theorem, max half integral flow min multicut theorem, which is also tight as is shown by this example here on the right. In this example, the minimum multicut is of size k minus 1. You have a maximum half integral flow which is k by 2 plus 1, and so there's a gap of a 2. So that's all I have to say, and well, I could have answered questions if this was in a room, but I guess I'll have to stop now. Thank you for your attention.